Hello everyone. Once again welcome to this Ch2-Lec e-learning channel. This is fourth lecture of this chapter, Special Theory of Relativity. In this lecture, we are going to derive Lorentz Transformation equations. Let us start. In first lecture of this chapter, we have seen transformation equations. The equations relating the two set of coordinates of the event in two frame of reference are called transformation equations. In that lecture, we have derived Galilean transformation equations, which are based on Newtonian relativity. And according to Newtonian relativity, time is absolute. Time is absolute. Therefore, in the Galilean transformation equation, t is equal to t dash all the time. But according to special theory of relativity, time is not absolute. Time depends on the frame of reference of the observer. Using that concept of special theory of relativity, we are going to derive the Lorentz transformation equations. To derive this Lorentz transformation equation, consider two frame of reference. One S. This inertial frame S is let it is at rest, and the another frame S dash, which is moving with velocity v along x dash axis with respect to the S frame of reference. That is, inertial frame S is at rest and S dash moving with velocity v along x dash axis. One observer is at rest in S frame of reference and another observer is in motion in S dash frame of reference. When origin of these two frame of reference coincide, let time t is equal to t dash is equal to 0. This t is the time recorded by the clock in S frame of reference and t dash is the time recorded in S dash frame of reference. When this origin O dash coincide with the origin O, then let this time t is equal to t dash is equal to 0, and let us assume at this time, that is at t is equal to t dash is equal to 0, at this time flash of light is emitted from the common origin. When O and O dash coincide, then the origin is common. Then at time t is equal to t dash is equal to 0, let flash of light is emitted from common origin of these two frame of reference S and S dash. During motion of this frame of reference S dash and the light, let at time t recorded by the S frame of reference, time t recorded by S frame of reference, and t dash recorded by the observer in S dash frame of reference, the light flash reach the point P. The light flash reach the point P. Then the coordinates of the point P with reference to S frame of reference are position coordinate x, y, z, and the time is t. And with reference to S dash frame of reference, the position coordinates are x dash, y dash, z dash, and time t dash. That is the time t dash required to reach point P from the origin O dash, and time t is a time required to reach the point P from origin O. As light velocity c is constant, according to special theory of relativity, Einstein special. In last lecture, we have seen Einstein postulates. According to Einstein's special theory of relativity, light velocity c is constant in any inertial frame. And here, these two frames are the inertial frame. Hence, the distance r is equal to ct. The distance of point P from origin, this r, c is the velocity, and t is the time required. Then velocity is equal to distance upon time. Therefore, distance is equal to velocity into time. Velocity is c and time is t. Therefore, r is equal to ct. and in S dash frame of reference, the time required is t dash and velocity is same, c. Therefore, this distance of the point P from origin O dash R dash is equal to ct dash. Also, this position R in terms of xyz, that position vectors, that magnitude R square is equal to, this also we have seen in the last chapter, that R square is equal to x square plus y square plus z square. This distance R square is equal to x square plus y square plus z square. And with respect to S dash frame of reference, R dash square is equal to R dash square is equal to x dash square plus y dash square plus z dash square. Then comparing these two, R is equal to ct and R square is equal to x square plus y square plus z square. Therefore, x square plus y square plus z square is equal to c square t square. Substitute this R is equal to ct. Then x square plus y square plus z square is equal to c square t square. And this here, substitute R dash is equal to ct dash. Then x dash square plus y dash square plus z dash square is equal to c square t dash square. These two equations. As the relative motion of S and S dash is along x dash axis, there is no change in y coordinate. In both frame of reference, y coordinate is same and z coordinate is also same. Therefore, y is equal to y dash and z is equal to z dash. If point P is located along x dash axis, if point P is located along x dash, along this axis, then y coordinate is 0 and z coordinate is also 0 along x dash axis. Y is equal to y dash is equal to 0, z is equal to z dash is equal to 0. If we substitute here y is equal to 0, z is equal to 0, then x square is equal to c square t square, or x square minus c square t square is equal to 0. Y dash 0, z dash 0. Therefore, x dash square minus c square t dash square is equal to 0. These are the two equations. X square minus c square t square is equal to 0 and x dash square minus c square t dash square is equal to 0. Right hand side same, therefore left hand side must be same. Therefore, x square minus c square t square is equal to x dash square minus c square t dash square. Let this equation 3. We have to find x dash and t dash in terms of x and t. We have to find the position coordinate x dash in terms of position coordinate in S frame of reference x and t dash in terms of x and t. Therefore, this x dash is function of x and t dash is also function of x and t. Then consider this simple relation, the relation between x dash, the position coordinate in two frame of reference S and S dash, x and x dash, in simple form may be written as, in simplest form they may be written as x is equal to k dash x dash plus vt dash, and x dash is equal to k into x minus vt. We have to find this constant k dash and k. We have to find this constant k dash and k. Substituting value of x dash from equation 5. Substitute this value of x dash here in equation 4. Substitute equation 5 in equation 4. That is, substitute this x dash in this equation. Then x is equal to k dash, this k dash. X dash is equal to k into x minus vt. This k into in bracket x minus vt, and this is vt dash plus vt dash. Then simplify this. Then x is equal to k dash, multiply this k dash to the first term, then k dash x minus vt, multiply by k dash to second term, then vk dash t dash. Then this vk dash t dash is equal to x minus this term. Vk dash t dash is equal to x minus k dash into x minus vt. We have to write this equation for t dash. Write this equation for t dash. Therefore, t dash is equal to, divide to the right side by vk dash. Then t dash is equal to x divided by vk dash minus xk upon v plus kt. which is equal to k. Take k common, then k is t, then here x upon vk dash k dash, x upon v into k dash, and here x upon v. K is taken common. Then t dash is equal to k in bracket t plus x upon v k dash minus x upon v. Then take x minus x upon v common from these terms. Then t dash is equal to k in bracket t minus x upon v is taken common. Therefore, t minus x upon v in bracket 1 minus k 1 upon k dash. This is t dash in terms of x v. We have to find this k and k dash. T dash is equal to this expression. Substitute values of x dash and t dash from equation 5 and equation 6 in equation 2. Substitute this x dash is equal to k into x minus vt and t dash is equal to this expression in equation 2. This equation 2, this x dash square plus y dash square plus z dash square. Substitute here this x dash and t dash here in this equation. In equation 2, substitute. Then k square x minus vt, this is x dash. X dash is equal to k into x minus vt. Therefore, this k square x minus vt bracket square plus y dash square plus z dash square into c square t square. This is the expression for t. Then t square is equal to k square in bracket t minus x upon v in bracket 1 minus 1 upon k dash with bracket square. As y is equal to y dash and z is equal to z dash. As there is no change in y coordinate and z coordinate, therefore substitute this y dash is equal to y and z dash is equal to z. Then simplify this, multiply this to this term x, square this term x square of the first term plus square of the second term minus 2 times product of these two terms using that rule, a square plus b square minus twice ab, a minus b bracket square is equal to, using that rule, this x square k square plus b square t square k square minus 2 times x v t k square. This is the simplification of this term. Y dash is equal to y, therefore here y square. Z dash is equal to z, therefore z square. Again use the rule a minus b bracket square, using that rule and simplify. Then we get c square k square t square plus c square k square x square upon v square 1 minus 1 upon k dash bracket square. This is the first term square plus this second term square, minus 2 times product of this first term and second term minus this x upon v and the second term. Then collect the terms of x, this here x, this term, and here x. Therefore, taking x square common from this term and this term, then k square minus c square k square upon v square 1 minus 1 upon k dash bracket square. X square is taken common. Then this is y square, here z square. Then this xt term, this 2 k square c square upon v 1 minus 1 upon k dash minus 2 vk square into xt, and the t square term, this one, here t square and this term, this two term, this here t square and here t square taken common. This k square v square minus c square k square, this t square taken common is equal to 0. Then from equation 1, x square plus y square plus z square is equal to minus c square t square is equal to 0. This equation, this is the first equation, x square plus y square plus z square is equal to c square t square. In this, use this equation and compare this equation 7 and 8. If we compare this equation, then coefficient of x square, here coefficient of x square is 1, therefore we get this first equation this first equation, k square minus c square k square upon v square 1 minus 1 upon k dash bracket square is equal to 1. Then here coefficient of y square this 1, z square 1. Then here there is no xt term. In this equation there is no xt term. Therefore this coefficient is equal to 0. 2k square c square upon v 1 minus 1 upon k dash minus 2vk square is equal to 0. This is second equation. And coefficient of t square is minus c square. And here coefficient of t square is this term. Therefore comparing the coefficient of t square we get third equation. This k square v square minus c square q square is equal to minus c square. Minus c square. This third term. In this way these three terms. This is a first term. This first term, which is a coefficient of x square. This coefficient of x square is equal to 1. This is first term. Then this second term here, this coefficient of xt. There is no xt term here, therefore this coefficient is equal to 0. This is the second term. And this third term. This third term is coefficient of t square. Here coefficient of t square is minus c square. Therefore k square v square minus c square k square is equal to minus c square. This is third equation. This way, these three equations. Then from this third equation, from equation number 11, from this equation, k square is equal to, here k square is taken common, then c square upon c square minus v square. This minus sign is taken common and cancelled. Then we get k square. From this equation we get k square is equal to c square upon c square minus v square. Or this equation may be written as divided numerator and denominator by c square. Then we get k square is equal to 1. Divide numerator and denominator by c square. Then at the numerator we get 1. C square upon c square is 1, and here v square upon c square. Therefore k square is equal to 1 upon 1 minus v square upon c square. From this we get the first value of the constant k. That k is equal to 1 upon square root of 1 minus v square upon c square. Let this equation number 12. K is equal to this equation. Let this equation number 12. And from this equation 12, this term is equal to, take this 2vk square to the right hand side. Then 2k square c square upon v 1 minus 1 upon k dash is equal to 2vk square. Divide by to the right hand side by this term. Then we get 1 upon 1 minus 1 upon k dash. 1 minus 1 upon k dash is equal to v square upon c square. If we divide this 2vk square by 2k square c square upon v, then we get v square upon c square. Therefore 1 minus 1 upon k dash is equal to v square upon c square, or 1 upon k dash is equal to 1 minus v square upon c square. 1 upon k dash is equal to 1 minus v square upon c square, or k dash is equal to 1 upon 1 minus v square upon c square. This k dash is equal to, but k square is equal to 1 upon 1 minus v square upon c square, because here k is equal to 1 upon 1 minus v square upon c square. If we square both sides, then k square is equal to 1 upon 1 minus v square upon c square. This k square is equal to 1 upon 1 minus v square upon c square. This right hand side same. Here 1 upon 1 minus v square upon c square. Here 1 upon 1 minus v square upon c square. Therefore k square is equal to k dash. Comparing these two equations, k dash is equal to k square, or k is equal to k dash. We divide this k to the right hand side, then k square upon k is k. Therefore k is equal to k dash. But k is equal to 1 upon square root of 1 minus, but k is equal to 1 upon square root of 1 minus v square upon c square. Therefore k dash is also 1 upon 1 minus v square upon c square. K and k dash, these two constant same. Hence this equation 6, this equation of t dash, substitute here k, this value of k, and 1 minus k dash. 1 minus 1 upon k dash is equal to v square upon c square, and k is equal to 1 upon square root of 1 minus v square upon c square. Substitute. Then t dash is equal to k into t minus x upon v, and 1 minus 1 upon k dash is equal to v square upon c square. Here v square upon c square. Substituting value of k, this value of k here. Substituting value of k in equation 5 and 16. This in equation 5. Equation 5 is this. X dash is equal to k into 1 minus vt. Here k is equal to 1 upon square root of 1 minus v square upon c square. Substitute here. Then we get expression for x dash. Get x. Substitute value of k in equation 5 and here also in equation 16. Then we get x dash is equal to x minus vt. X dash is equal to x minus vt. Here we substitute here. This k is equal to 1 upon square root of 1 minus v square upon c square. Then we get first expression, x dash is equal to x minus vt upon 1 minus v square upon c square. Y dash is same for the case which we have considered. Y dash is equal to y, z dash is equal to z, and t dash is equal to this t minus, if we simplify this, then we get xv upon c square, t minus xv upon c square, and this k is 1 upon square root of 1 minus v square upon c square. Therefore square root of 1 minus v square upon c square. Then these equations are known as Lorentz transformation equation from S to S dash frame of reference. From S to S dash frame of reference. Because on the right hand side, the coordinates are x and t, which are the coordinates of S frame of reference. Here also x and t, which are the coordinates of S frame of reference. And on the left hand side, this x dash, y dash, z dash, t dash are the coordinate of S dash frame of reference. Therefore, these equations are known as Lorentz transformation equation from S to S dash frame of reference. That is, if we know the coordinates x and t and velocity with in S frame of reference, then we can find the coordinate in S dash frame of reference using this transformation equation. Then inverse Lorentz transformation equations, that equations from S dash to S frame of reference. Equations from S dash to S frame of reference are obtained by replacing v by minus v. The equations, Lorentz transformation equation which we have just derived, in that equation replace v by minus v and interchange prime and unprime coordinate. Prime and unprime coordinate. That is, replace this v by minus v. Then here we get plus. Then replace this x by x dash, t by t dash, and this x dash by v. Here also y dash by y, y by y dash, z dash replaced by z, and z replaced by z dash. Here t dash replaced by t. This t is replaced by t dash, x is replaced by x dash, and this v is replaced by minus v. Then this sign becomes plus. Then we get this equation, x is equal to x dash plus vt dash upon square root of 1 minus v square upon c square, y is equal to y dash, z is equal to z dash, and t is equal to t dash plus v upon c square x dash upon square root of 1 minus v square upon c square. These are equations from S dash to S frame of reference. S dash to, because on the right hand side the coordinates are x dash and t dash are here also. X dash and t dash are the coordinate of S dash frame of reference. On the left hand side, x, y, z, t are the coordinates of S frame of reference. So these are the equation from S dash to S frame of reference. Then observations from this Lorentz transformation equations. The first observation is the measurement of time and position depends upon the frame of reference of the observer. Here, this position and here time depends upon the frame of reference of the observer. In Galilean transformation, the time is independent of the frame of reference. But in Lorentz transformation, the time depends upon the frame of reference of the observer. This is the first observation. And second, when v is very, very less than c, that the velocity of the frame of reference is very less as compared to the velocity of light. If this velocity of the frame of reference or the observer is very less as compared to the velocity of light, or object velocity is very less as compared to the velocity of light, then this v upon c square is negligible, or this v square upon c square, because denominator is very high as compared to large as compared to numerator. Therefore, this v upon c square and v square upon c square tend to 0. Therefore, this term tends to 1, that 1 upon square root of 1 minus v square, this is 0. Therefore 1 upon 1 is 1. Therefore this denominator in both equations, this denominator tends to 1, and this v upon c square tends to 0. Therefore this term becomes 0. Therefore t is equal to t dash, t is equal to t dash, and here also this term tends to 1. Therefore x is equal to x dash plus vt, or x dash is equal to x minus vt. X dash is equal to x minus vt, and t dash is equal to t, or t is equal to t dash. Then x dash is equal to x minus vt, y dash is equal to y, z dash is equal to z, t dash is equal to t. And these are the Galilean transformation equation. Therefore, at very low velocity as compared to the velocity of light, the Lorentz transformation equations are converted into or reduced into Galilean transformation equations, because these are the Galilean transformation equation. That's all in this lecture. Thank you.